understanding the relation between, exponential growth and logarithmic scales. All right. So for any positive number, let's call it x, the natural logarithm or the logarithm base e of x is given as, or is given by natural log. As you mentioned, is equal to this. Okay. So let's take note. So we claim that the x is any positive number. Okay. And then if that's the case, then the natural logarithm or the logarithm base e of x is given as this. And we claim that such an equation can also, for example, if I claim that y is equal to the natural logarithm of x, then this can be written as, so I can use a different pencil. This can be written as this. So let's take note. So this can also be written as e to the power y equal to x. Why do we say so? Why do we say that these two are the same? Why do you say they are equivalent? Why do we say so? Remember, we said that ln of x can also be written as what? From here, we claim that ln of x can also be written as what? Log base e of x. Okay, log base e of x. So log base e of x. Now, if I have this, so this is how we do it. So if I have this such an equation, what it means is that I can sort of solve for x, right? So this is almost as if e would be raised to the power y. Okay. So by letting e, raised to the power y, we're going to have x to be equal to what? E to the power y. So that's how come we have this. So I want us to take note. Okay, good. Now let's shift our focus to derivative. And as I mentioned, derivative, we said that is a what? Is the rate at which a function is changing over time or is changing at some point. So please let's take note of that. It is very, very, very important. So please let's take our time to understand the basis. Now let's look at the first theory. So the first theory is that if x is positive, so for any positive number, let's call it x, okay? For any positive number x, then we claim that the derivative of the natural logarithm, or what we term as ln x, will be given as what? As 1 over x. So how did we get this? So this is how we did it. This is how we kind of solved it. What we did was that we kind of covered the lane. It's almost as if we are blind to this symbol, which is the lane. Okay, we are blind to it and we differentiate x. So when we differentiate x, we get what? 1, right? When we differentiate x, then we divide it by the input of len of the function x. Okay, so anytime I ask you to find the derivative of x, we get 1 out of x. So please let's take note. So that's the tricks we use in kind of solving problems that relate to issues like this. Okay, so let's take note. Good. All right. So let's move on. Now, if I give you, suppose I say to find dy dx, if one y equal to 5, then x. B, let's say y equal to, let's say, x to the power 3, then x plus, let's say, 4e to the power 2x. Okay, good. How do you solve a problem as this? How do you solve a problem as this? Now, the first problem, we have y equal to 5 multiplying the natural log of x, right? Good. So what we do is that we kind of differentiate both sides, okay? So we apply derivative on both sides. So by applying derivative on both sides, we're going to have something as this, okay? Now, we said that so 5 is just a constant, which means we can just put it outside, right? Now, we claim that when we differentiate the ln x, we get what? 1 out of 5. So in that case, we're going to have 5 multiplying 1 out of 5. And this is the same as this, right? Good. Now, what about the b? With the b, we're given y equal to x to the power 3, or multiplying natural log of x plus what? 4x. Now, how do we differentiate this? So we kind of apply, derivative of both sides, and applying derivative of both sides, you should get, this is the first thing to do, okay? Now, how do we differentiate this? We could see that now by applying the sum rule, so it means in which case we are going to differentiate this by using the sum rule, right? The sum rule. Now, but then you could see that this is product of two functions, right? In which case you will have to apply the techniques I keep telling you. You cover one function, differentiate the other, plus you cover the other one, the next one. So that's the same thing that we apply here. So first, let's covered x to the power 3, and by covering x to the power 3 and differentiating ln x, you get what? 1 out of x, okay? Plus what? Plus we kind of, covering ln x and then differentiating, okay, let me take my time, okay? Let me take my time over here. Let me take my time so that we do it step by step. So we first cover this and differentiate ln x, okay? Then now we cover ln x and then differentiate with x to the power 3. I hope we are okay at this point. Good. So what I did over here was to apply the product rule. So that's exactly what I did. All right. So let's take note. All right. Now, when we, differentiate the ln x, what do we get? We get 1 out of x. All right, good. And then when we differentiate x to the power 3, we get what? We get 3x to the power 2, or multiplying natural log of x. What about it when I differentiate 4x? What do I get? I get 4. Good. So at this point, you can do your, simplification, then you get a final result. And the final result, this cancels that. Then if you get what? X squared plus 3x squared natural log of x plus 4. You can still go further to do your simplification. Okay, so let's take a look. So at this point, if you have any questions, please let me know, and so that we could kind of understand it better. If you have any questions, just put in the comment section. And at this point, if you have not subscribed, please do subscribe, like, comment, and then share the content to your colleagues who are also struggling in mathematics. Okay, let's keep this knowledge spreading to be a blessing unto others. So I want us to look at the last, theorem of the day, and the theorem has to do, it's just an extension of the first theorem that we did. Okay, so let's go to the last theorem. Now the last theorem of the day says that if I'm to differentiate the natural log of another function, okay, this time not x, not the natural log of x, but right now the natural log of another function. How do we do that? Okay, so that's the goal of today's that's the goal of this theorem. So this theorem says that what we do is that now differentiate the input. Okay, so the theorem says that if I'm given such a problem to solve, what for us to solve this, the easiest way to solve this problem is that now differentiate the input. What's the input in this problem? The input is what? F of x. So the theorem is saying is that differentiate the input. So by differentiating the input, in other words, your f of x, okay, then we divide it by the input. So that's what the theorem is saying. Very simple. You see, it's very simple. Very, very, very simple. So this can also be written as well. Because when you differentiate f of x, you get what? F prime of x. So this is the theorem. Very simple. Okay. Very, very, very simple. So I think this is a very important theorem that you don't want to miss. I want to make sure that you understand the theorem very well, because we're using them to solve problems. Good. So if that's the case, let's look at some basic examples. Okay, so some examples. If I ask you to find the y, the x, or change in x, respect change in y for this case. Let's say the first case is y equal to this. How do you find the derivative? And then the b, if I give you y equal to the natural log of x to the power 2 minus 5, and then the c, f of x equal to the natural log of the natural log of x, and the d part says that, and the d part is f of x equal to the natural log of x to the power 3 plus 4, all divided by x. How do we solve such problems? So the first problem of the day is y equal to natural log of 3x. Okay, good. How do we solve this? What does the theorem say? Now, the theorem we just learned was that by solving such problem, what we do is that we differentiate the input. So our input in this problem is 3x, okay? Then we divide it by the input. So the theorem is saying that differentiate the input and divide it by the input. Differentiate the input divided by the input. This is very interesting, right? Good. So in that case, when you differentiate the input, you're going to get what? When you differentiate 3x, what do we get? 3. Then we divide it by the input, and that gives us what? So when you do your cancellation, you should get what? 1 out of x. Very, very important. Good students. All right. The b part. Now the b part, we have y equal to the natural log of x to the power 2 minus 5. And when we differentiate this, what do we get? We differentiate the input, okay? We differentiate the input, then we divide it by the input. And when you differentiate the input, what do you get? When you differentiate 2x minus 5, when you differentiate 2x, you get what? 2x. And you differentiate minus 5, you get what? 0, because the constant, okay? Divided by the inputs. See, it's very simple. Good. Now, what about this? The C, we have f of x equal to the natural log of x. And that gives us what? So according to the theorem, it says that for us to differentiate this, we differentiate the input and divided by the input, right? Now, what's the derivative of the input? Which is what? One out of x or divided by this. Good, 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 good. So this can further be written as what? 1 over what? X multiplying this, right? Good. What about the D? As to do that, what do you get? Who has already solved it? So with the D, we have f of x equal to the natural log of what? X to the power 3 plus 4 all divided by x. Okay, good. In that case, so to differentiate this, we claim that we kind of differentiate the input, and the input in this case is what? X to the power 3 plus 4 all out of 3 all divided by the input. Okay, so let's take notes. Very, very important. Now, when we differentiate the numerator, what do we get? So we use what we call the chain rule, right? We use the chain rule. And what will you get if you do that? What do we get? All right. So this, for us to solve this, I would say that, there's a law that I want to draw your attention to. All right. So one of the principles of natural logarithm function is that the logarithm of, or the natural log of a, okay, I want to draw attention that, so for instance, if I give you problems that has to do with quotient, okay, and I ask you to find, so if I give you, logarithm functions of logarithmic function that relates to, okay, and I ask you to find the derivative, okay, usually what we do is that we apply one of the laws of logarithm functions. One of the laws is that the logarithm of this quotient, okay, is the same as what? The natural log of a minus what? The natural log of b. So please, let's take notes. Okay, good. So with that, so it means that we don't have to go through this, because if you want to use this, it means you have to use the chain rule. Probably you may not, sorry, the quotient rule that relates to derivative is something you may not be able to recall all of that. So I don't want us to go through this route. You could do it, but that will be long. But then if you apply this principle is very straightforward. Okay. So I want us to borrow the principle over here. Good. So with that being said, we're going to have, so first let's apply the principle here. So in which case we should have the natural log of x to the power 3 plus 4 minus natural log of x. Good. Now this becomes so simple to solve, right? So it means that my first derivative, now the derivative of this, we claim that we differentiate the input of the first function, and that gives us what? The input is this, and divided by a, minus we also differentiate the input divided by a. Okay. Now when you differentiate the input, what do you get? 3x to the power 2. And when you differentiate the constant 4, we get what? 0. Then we divided by this minus. And when you differentiate x, what do you get? 1 divided by x. So this is that. But then you can go further to simplify. And when you simplify, you should be able to get something like 2x to the power 3 minus 4. Is anyone having an issue here? If you have any issue, please again, let me know, then I will address that. All right. So this is what we are supposed to get. At this point, if you have not, subscribed, please do so by liking my video, sharing it, and let's spread the news. All right. So I would want us to look at situations where we can apply the logarithmic functions. So today, the first, practical problem of the day is given us as this. So in a psychological experiment, students were shown a sort of nonsense syllables such as POK, RIZ, DEQ, and so on, and asked to record them every minute thereafter. The percentage, which is in terms of R of T, who retained the syllable after T minutes, was found to be given by the logarithmic learning model. And we claim that the time is within 1 minute to 15 minutes. So I want us to take notes. Now, the first one of this is that what percentage of students retain the syllables after 1 minute? And then the final problem is that we should find R prime of 2 and explain what it represents. Okay. This is a very interesting problem of the day. So please, let's look at how best we can solve this problem. All right. Now, so we are given this, logarithmic learning model. So the model is giving us R of T equal to 80 minus 27 natural log of t. Mind you, the t, I said it's within 1 minute to 15 minutes. Okay, so please, let's take notes. Now, the question says that what percent of students retain the syllables after 1 minute? So after 1 minute, we claim that after 1 minute, we're going to have 80 minus 27 multiplying the natural log of 1. And that result should give us what? If you use a calculator, that should give us what? That should be 80%. Okay, that should be 0.8. So that's 80%. Now, what about the B says that we should find the R prime of 2. So R prime, for us to find the R prime of 2, so we first have to find the R prime. So R prime of T, so in other words, changing the logarithmic learning model with respect to time, okay? So how this logarithmic linear model is changing over time. That is the R prime of t. That's what it means. Okay. So in which case we're going to find the derivative. We're going to apply the derivative on both sides. Okay. So by applying the derivative on both sides, we are going to have now what's the derivative of the constant 80? And that is what is 0, right? You can have 0 minus 27. Now what is the derivative of 1? What's the derivative of length t? And that gives what? 1 out of t. So in which case you're going to have minus 27 out of t. Okay. But the question was very specific at time 2. So at time 2, at t equal to 2, in other words, wherever you see t, you should replace it by 2. Wherever you see t, we should replace it by 2, in which case that would give us all the 13.5. But what does this represent? The question says that we should explain what it represents. So this means that this value means that 2 minutes after the student have been shown the syllables, the percent of them who remember the syllables is shrinking at the rate of 13.5% per annum. Remember what I said, shrinking. Shrinking represents what? The minus. So this minus implies that there's a decay. Okay, there's a decay. So let's take note of that. All right, so at this point, if you have not subscribed, please subscribe, like, comment, and share my content to colleagues who are struggling in mathematics. Let's come together as a community. Together we'll be able to kind of have a community where people will be moving to STEM and all of that. Please have a foundation that also is into helping students, who wants to upskill their learning, who wants to upskill themselves in the. So please join me even as we explore this journey together. All right.